No, we were just discussing that probably we will not be able to do too much of magnetodynamics, electrodynamics. I mean, we have, I think, after this week, we have 4 more weeks. Today, I'm hoping to finish magnetic dipoles in the remaining half an hour. And then we have, next week, we will do magnetic fields in matter. And, well, I mean, if we can finish magnetic fields in matter next week, we will have 3 weeks we can start electrodynamics. At least 1 week we will spend on obtaining the Maxwell's equations in an electrodynamic case. And then we will have 2 weeks to go over what are the consequences of light. We can go over reflection, refraction of light. That's one thing I would like to do. And probably that would be it. Okay, let's continue. Any questions on this one, on the derivations? So let's look at the magnetic dipole. We have this vector potential expression, which we wrote as JR prime over R minus R prime integrate over a volume V. Now, it just looks like the expression of the electrostatic potential, as we stated before, with the replacement of the current density with the replacement of the charge density with the current density. That's the only difference. So whatever we did in electrostatic potential, we can also do it over here. One of the things we had done, if you remember, was this multiple expansion, which basically we started by considering this factor and assuming that R is much, much larger than, let's say, D, where we have this region where we have all these currents running around, static currents, their divergence should be 0, and D is basically the size of this region. And this is our origin, this is the point, so this is the R vector. So you choose some point in your region of the current, some points in your region of the current. You are observing your current at a faraway point. Now, these currents can be, for example, the currents in an atom. The electrons are, semi-classically, the electrons are constantly in motion, so they have a current. They create a current, but that's localized inside the atom. You don't have any current outside, but inside you still have the current. Or the spin, again, you can, semi-classically, let's say, you can consider the spin as a charged object rotating, just like our previous case. A charged object that is rotating, so there will be internal currents over there. Of course, this is not the correct quantum mechanical description, but still classically, semi-classically, you can visualize it in this form, as a rotating sphere. Now, in this case, we had seen this expansion, and we saw that this was equal to sum over L and M, R prime to the L divided by R to the L plus 1, Y L M of omega, Y L M of omega prime. This one of them being conjugate. Now, we won't be dealing with all these moments, just the dipole. So for the dipole case, for us, it will be enough to take this as 1 over R times 1 plus R dot R prime over R squared. Well, to see where this comes from, 1 over R minus R prime is basically the square root of R plus R prime squared minus twice R dot R prime. Now this is R squared. R squared is, R is the large one to the power minus 1. So let's just take the R out, so this becomes 1 over R, 1 plus R prime squared over R squared minus twice R dot R prime over R squared to the power minus 1/2. And this is approximately 1 over R, 1 plus r dot r prime over r squared. So it's just the binomial Taylor expansion. I just ignored all the terms that are proportional to r prime squared over r squared. Now, if you make this expansion, the vector potential becomes J of r times 1 over r plus r dot r prime over r cubed dv prime, J of r prime, sorry, 1 over r times J of r prime dv prime plus, sorry, in the vector potential we have this 1 over c factor also. Plus 1 over r cubed c in the r hat direction, or 1 over r cubed c j r prime r dot r prime dv prime. This is the general expansion of the vector potential. Now let's do one thing. Let's look at this first term. I will claim that j r prime dv prime is equal to 0. To see that that is actually 0, let's look at the components of this one. Ji, well, let me put the ji prime, meaning that it's evaluated at r prime dv prime. This is equal to xi jj derivative with respect to xj prime dv prime. You see, if you take the derivative of xi prime with respect to xj prime gives you a Kronecker delta ij, and that gives you ji prime. Then there is the derivative of xi prime multiplied with the derivative with respect to xj of jj prime. That is the divergence of j, which is 0. Or let me rewrite it, write it explicitly. This is equal to Kronecker delta ij jj prime which is equal to del over del xi prime xj prime xi jj prime, or let me even add one more step here, xi xj jj prime. That derivative is nothing but the Kronecker delta. This is equal to derivative of the product of xi prime with jj prime minus xi prime derivative of jj prime with respect to xj prime. Now this is nothing but the divergence of j, which is equal to 0. Now let's look at the first term. The first term is nothing but the divergence of xi prime times j prime but it is nothing but, I can write it as a surface integral my surface is at infinity. The current is localized, there is no current at infinity, so that surface integral is 0. Yes?
Do we have del xi prime j prime by del x j prime? Or
Where? There.
yes.
Yes?
Do we have prime?
Yes, 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 these are all prime coordinates. This is also gradient prime with respect to r prime. Now let's look at the second term. So the first term is 0. Now let's look at the second term. A is equal to 1 over CR cubed integral of J prime R dot R prime, all right, dV prime. 1 over CR cubed. Now look at this identity. R cross J prime cross R prime. This is equal to J prime R dot R prime. Okay, this is what I want. Minus R prime dot R dot J. So the vector potential, now I can write it as 1 over CR cube. No, sorry, this is minus, yes. Of R cross J prime cross R prime, dV prime, plus 1 over CR cube, R prime dot R prime times R dot J prime dV prime, which is equal to 1 over CR cube R cross J prime cross R prime dV prime plus 1 over CR cube R prime R dot J prime dV prime. Now what I will call the magnetic dipole moment, this is the definition of a given current distribution, will be 1 over CR cube R prime cross J prime, integrate over the volume, over all space, not the second term. So I end up having A is equal to, no, there is no R cube, 1 over C. Mu cross R over R cube. Well, you see, in the definition of the magnetic dipole moment, I exchange the position of R and J. You see here in this integral over here is J cross R, but in the definition it is R cross J, so that gives a minus sign. But I have this R cross this integral, so I also exchange their positions, so that also gave me another minus sign, so I have the mu cross R. So that's why I don't have any minus signs, etc. Plus 1 over CR cube R prime R dot J prime. Now the first term is what we call the magnetic dipole contribution to the vector potential. In fact, that is what I had claimed in our previous example. That's R hat over R squared. This is R over R cubed. So your homework 2, calculate mu for the rotating sphere example. Well, there will be an easier way than just trying to evaluate this integral. We will discuss after we show that that second term over there is 0. So let's see, that term, we can write that integral. Let's look at that integral. This is equal to Ri, R prime Ji prime. Now what I will try to prove is Rj prime, Rj prime, Ji prime, dV prime, this should be equal to 0. Or let me write this, xj prime. This will be my purpose. Eventually. Let's go back to the definition of the magnetic dipole moment first. I mean, today I will be able to prove that, simplify this expression. I mean, this is the magnetic dipole moment for a general current. Now you have already remembered I hope you still remember in your first year, even you in 105, you defined the magnetic dipole moment of a loop as the area times the current in the loop. But that was assuming the loop was on a plane. So if it was bent, it doesn't hold anymore. So let's see that this is the generalization of that expression to arbitrary currents. The current need not be on a loop, on a plane. This is still correct. But let's see that they match. We define the magnetic dipole moment as 1 over c r prime cross j prime dv prime. Now, for a current carrying loop in a plane, let's say this is our origin. This can be written as 1 over c r prime cross dl times I. Again, j prime dv, dv prime, this just goes to I times dl in the case of a current carrying wire. Now let's look at what these dl's and I and r prime will be. Now this is my dl. This is my r. Both of these are kind of equal to r prime. Or let me just take one of them. This is my r prime. Or in fact, let's just consider any two vectors, A and B. Now, what's the magnitude of A cross B? This is AB sine theta. Let me consider this triangle. This height of the triangle is nothing but A sine theta. Remember, this is theta. So if you just, this is just twice 1 over 2 A sine theta times B. But 1 over 2 A sine theta times B is nothing but that area over there. Twice the area of triangle. Well, the same thing holds over there. If you consider this area is equal to twice r cross dl. No, 1 over 2 times r cross dl, or r prime cross dl. So mu is equal to I over c I times r cross dl. You see, since this is on a plane, r is always in that plane, dl is always in our plane, so r cross dl is always perpendicular to this plane, but the perpendicular to this plane is constant. Since r and dl, they are always in the same plane, the perpendicular direction to the plane will be constant independent of r prime or independent of dl. So that r cross dl is nothing but twice 1 over c, well, let me also take the I out, area, the area in the n direction. Well, if you just sum those areas, you have 2 over c I times the area. Now, this factor of 2 over c is due to our definitions and the units and the conventions. So it's again the current times the area, as you probably remember from your freshman years. But as I said, this is for an arbitrary current. Now, for an arbitrary current that is not in a plane, what will happen is that this n vector will not be constant. So we will not be able to take it out of that integral. And since we will not be able to take it out of the integral, the magnetic dipole moment will not be the current times the area. Now, the only thing left in our treatment is to show that the second term is 0. This one. Well, the trick will be basically the same. We will just put some Kronecker deltas, etc. This is xj, xi. We already had seen that ji prime is actually the gradient of xij, no, the divergence of xij. To prove it, this is just nothing but the gradient of xi. Or let's see. This is del over del xj, xi times jj. This is derivative of xi over xj times ji, jj, plus xi times del jj over del xj. This is just 0. It's the divergence of j, which is 0. This is Kronecker delta ij. So this is just sum over the j's, you get ji's. Of course, there's always primes in our case. So instead of that ji prime, we can just replace that gradient. Well, let me not rush this. Just play with this idea to try to prove that the above integral is actually 0. On Monday, we will start with that one. And once we prove that, then we have this multiple expansion. A is just equal to this one. For any current density sufficiently far away from the region which contains the current. Well, actually, this is one simple description of the Earth, the magnetic field of the Earth. So we know that Earth has a magnetic field in the atmosphere, even in the sky, in space. That is what is protecting us from the solar winds, which are high energy charged objects. And they are, one simple model is to assume that in the core there are these currents running around the sphere, which creates this dipole. So at least to describe these magnetic fields in space, we can just approximate the Earth as a dipole with a given dipole moment. Well, the picture is more complicated than this. I mean, if you look at the details, the Earth, on the surface of the Earth, we don't really have two poles. There are other poles in other places. They are much weaker, so the magnetic field lines, they don't start from the north and go from the south and go to the north. There are some other places where they enter, they leave, etc. It's not such so uniform, but a crude model would still be just a single dipole as a rotating sphere inside, at the core. And it seems that this dipole is rotating with time. So the magnetic north and the magnetic south in the history of Earth, they just flipped several times. And the reason we don't really know. We don't have an answer for why does it flip. Any last minute questions? So see you on Monday. You already have one homework that was due today. Okay, bring it on Monday. You have your second homework. Even if I don't prepare the PDF for your homework, those two questions are still your homework for the next Monday.